Okay, hello and welcome to Unit 7 of the NLP course. This is the unit for March 26th, which is technically Unit 7. So last time we were starting with our introduction to PyTorch, and we had a look at the first two parts of the online tutorial. So we are using this online tutorial, which you can see here, and we had a look at introduction to PyTorch and to deep learning with PyTorch in the last unit. Let's have a very quick reminder and repetition, because we need what we learned in this first two parts now in the upcoming sections. In the first part, introduction to PyTorch, it was the introduction to the tensors, so the basic data structure used in PyTorch, and we looked at different operations on tensors. We learned how to create tensors, how to concatenate tensors, to reshape them, to add them, so this just basic operations on tensors. And then in the last part of this part 1 of the tutorial, there was a discussion of computation graphs. And computation graphs are basically how you build your neural network structure. So how you get from the input in various steps, various network layers, various operations, to the output. And the most important issue here is how do you train the model, how you can learn. And here PyTorch helps you with automatically doing differentiation on this on the loss, which we'll discuss later, or based on the loss, which you can then use to update your network weights to learn in the training process. And then secondly, last time we had a look in the second notebook, Deep Learning with PyTorch, at how to build and how to train a simple network. And for this we used a feed-forward, so a very standard network, which basically has, as all deep learning models, like a vector of numbers as input, and then did a matrix multiplication on this vector to create an output. So this is also called using affine maps, which just represent the parameters which are used to transform the input to an output using this matrix multiplication. Then we also saw how to use nonlinearities. Nonlinearities are very important to make your machine learning model more powerful. So there has been some theoretical work a long time ago. I think it's called the global approximation theorem, which proves that by the combination of multiple linear and non-linear elements in your network, you can basically approximate any mathematical function, also very complicated functions. And the non-linearities are crucial to make the algorithm more powerful, so to learn more complex functions. Yes. Then in this second part we also quickly discussed loss functions, so which just basically tell you how far your predictions are away from the real expected result of the network. And with the loss function you can quantify the error of your predictions and then use this to train your model. And then one last thing which we also had there was the softmax function, which is typically applied as a on the output, on the last layer, to give you a probability distribution over the output classes. And the softmax function, the probabilities, they add up to 1. So the probabilities of all predicted classes, they add up to 1. So softmax gives you this probability distribution. And then we also built a simple neural network in this part. And let's just have a quick look before we start with the new content on what is called the training loop. So how do you, when you have defined your network and you have read your input data and everything, how you train the network. So the training loop, which we can see here, so you have usually a loop outside on how many epochs, how many times you want to go over the data to train. And then you iterate over the training instances and the labels, which are used to quantify your error. Then usually you have to zero the gradients so that you don't keep any gradients from your last computation. Then here we read the input data and transform it into tensors, which are then suitable for TensorFlow. We feed those this input tensor into the model, and we get some probabilities of the output classes. And then we can use those probabilities, compare them to the target, so the labels which we would expect, and have the loss function quantify how far we are away from the target for each class. And with this information we can then call this backward step, which does the differentiation, so it computes the gradients on how to change the weights, and in the optimizer step we finally change the weights depending on our learning rate. The changes are bigger or smaller, so that the network learns faster or slower. But it doesn't, this now sounds like it would always be good to have a high learning rate. If the learning rate is too high, then maybe then the network will jump too far in this learning landscape, and it will not learn properly. So the learning rate, it has to be also balanced. Okay. Good, that's the repetition part, and we can now start with the new content for this unit.